Today we have final review lecture, and so first part of the lecture it will be some review of what we have learned this term, and then I will continue my talk about approximations, about exchange correlation approximations, and I will tell you about MetaGGA and hybrid functionals. So first part of the lecture, I hope it will be easy and familiar to you. And I will start with Born-Oppenheimer approximation. So what is the point? Why do we need density functional theory? Because we can't solve Schrödinger equation. If we can solve Schrödinger equation for systems higher than hydrogen and in some cases helium, we don't need all this stuff, but we can't do it. So we need some approximations. First approximation is the story. It's not the first approximation generally, but in this story, it will be Born-Oppenheimer approximation that we can split Schrödinger equation into two parts, into electron part and ions part. And what we have here, we have electron part. Here we have kinetic energy of electrons, electron repulsion, interaction between electrons and nuclei, and psi function that contains all electrons and their interactions with nuclei. And we have nuclei part, kinetic energy of nuclei, nuclear repulsion, and some potential in which all this stuff exists. And then we say that nuclei, they are much heavier than electrons. That's why we can neglect this part and solve only this part. So we have simplified the problem. We removed all these nuclear terms from the equation. And then this approach was used by Hartree to create his method. And he moved further. He thought that we can take this electron Schrödinger equation, but we still have very huge, very complicated psi function with a lot of variables. And then we can split it into just product of independent one electron psi functions. And the Hartree method reduces Schrödinger equation problem to just some system of one electron equations. Here you see this one electron stuff, kinetic energy of electrons, external potential which created by nuclei, and so-called Hartree term. Hartree term, what is Hartree term? I think you already know what is it. So Hartree term is interactions between electron and some mean field of all other electrons. So we can say that it's interaction between electrons and electron and all other electrons. So here is external field. It's created by nucleus, and Hartree term created by all the field of all the electrons in the system. And E, it's energy eigenvalue or energy of some one electron state. So we have split our Schrödinger equation into some into a lot of simple parts. And then Fock improved this method. He have told that in original Hartree method we can't include fermions because fermions should be antisymmetric. When we change products of these wave functions, we had to change the sign of the whole equation, and we can achieve it by using not a simple product as Hartree suggested, but this determinant. And in the determinant, when we exchange, for example, some columns, we will change the sign of determinant. That's why it makes the system antisymmetric, and we can calculate fermions. And from this upgrade, we got two new integrals in the energy. So I have shown you just Hamiltonian, which was very simple, as I think. So here is only Hamiltonian part. And now when we use Slater determinant, we have also this Coulomb integral and exchange integral. What is Coulomb integral? You see, it's just Coulomb interaction between electrons. Function of some electron and point x1 complex conjugated, and the same for another electron. So it's electron density for one electron, electron density for another electron, and we see their interaction. That's why it's called Coulomb integral. And then we also have exchange integral. It's some simple thing if we look at it from this point of view, from point of view of psi functions, because in Coulomb integral, we just in this exchange integral, we just moved, for example, this psi g function to here and make it mixed. So we have here not psi function of one electron, but we have psi function of one electron and psi function of another electron in the same point x1. And here we have the same for x2. And this integral it's rather hard to calculate this integral, and it creates exchange energy, and it grows from antisymmetry of fermions. When we include fermions, we get this exchange correlation. So this is this is quantum effect. This is the whole quantum effect, and there is no exchange in classical systems. And then it was another model, Thomas-Fermi model. In this model, we moved from electron psi functions to electron density. It had very is a very good, very efficient influence on the system, because we moved from the system of n, where n can be very, very huge. Of n variables, we can go to only 3 variables, x, y, z, because n electron density is something which we can measure by some techniques. So it's something which exists in our 3D world, not in some Hermitian space. Here, so what is the kinetic and potential energy in Thomas-Fermi model? Kinetic energy is so-called local density approximation. We take some point in the space, we take some space near this point, and we say that density in this space don't change. It's stable. And we can, that's why it calls local density approximation. And it goes, if we will make this assumption for electron gas, this all works only with electron gas, we will have this equation. So this integral is the integral of kinetic energy of electrons in a homogeneous electron gas. Homogeneous because in each point we have the same density. Energy functional for electrons interactions will be Hartree energy. Here we have not electrons, but we have electron densities. It's the same. So we have one electron, another electron represented by electron densities. And that's why we can say that it's just electron repulsion. It's very easy. Kinetic, potential energy. And total energy, in total energy, we also include interaction between electrons and external field of ions. So we call it external field because we don't want to include each ion in the equation. And we have this equation. It's energy in Thomas-Fermi. And this energy, this is functional because it's some function which depends on function. And it depends on electron density. That's why it is some ancestor of density functional theory. And density functional theory. Hohenberg covariance and Kohn-Sham equations. Kohn theorems we can simply they simply state two statements. So all properties are determined by electronic density, and the energy functional of ground state is determined by electronic density of the ground state. They took that Thomas-Fermi energy functional and told that if it will be ground state, so ground state is the lowest energy of the system. In all our calculations, we have calculated ground state. It's harder to calculate not ground state, but it's rather easy to calculate ground state thanks to density functional theory. When we get an energy function of ground state, we can so it depends only on electronic density of the ground state. So ground state to ground state, nothing more. But this theorem they was very important. But they didn't show us some way how to apply them to real systems, to calculations. And this way have shown Kohn-Sham equations. So they substituted the real system with some system of non-interacting electrons. And but it was the problem that we don't know that exchange correlation energy. So what is the algorithm? We use this algorithm each time when we start our quantum expressor calculation. It consists of this circle. It's rather simple to me. We start from some guess of electron density. We can take this guess from some potentials to combine these potentials and create this electron density. It will be very root, and it's not the solution. And then we should improve this guess by this cycle. So we compute Kohn-Sham potential. This is one of Kohn-Sham equations. So what is Kohn-Sham potential? It's some effective potential which consists of external field, external potential, of Hartree energy, of so it's Hartree potential. It means the potential created by mean field of all electrons. And it affects on some electron we calculate in the cycle, plus exchange correlation potential. So this exchange correlation potential, it rises from that exchange energy which we saw in Hartree-Fock method, and correlation is the all other energy which we just discarded when we calculated kinetic energy in Thomas-Fermi. So it was local density approximation, but it's approximation. It's not the real kinetic energy. And the difference between real kinetic energy and that approximation is correlation energy. We can't say much more information despite I have told to you. So it's different between real kinetic energy and some kinetic energy approximations. We compute this Kohn-Sham potential using this guess of electronic density. Then we solve one electron equations. One electron equations is just simple Schrödinger equations for each electron in the system. And here we have energy of each electron. And then we create new electron density. We get psi functions from here. Then we just calculate this psi function and calculate electronic density. Then we compare electronic density with this electronic density with previous electronic density and say that if it satisfies some condition, some threshold condition, then we stop the calculation and we get our energy. This is when quantum espresso writes job is done. If not, we go on some other side. So I think it's rather clear. And on the previous lecture, we have focused on this Kohn-Sham equation, one electron Kohn-Sham equation. It divided, and I have told you in more details about each of the terms. So about and how they applied in calculations, in real calculations. About kinetic energy. So we can have few approximations. We can have non-relativistic approximation. It's just Schrödinger equation. Something happened. We can have full relativistic when we include spin orbital interactions. And we can also have scalar relativistic approximation. It means that we should solve not Schrödinger equation, but Dirac equation, where only kinetic energy will be relativistic, but we don't include spin orbital interactions. So next term, we'll consider this full relativistic methods for spin orbital interactions, and we will see that it gets even for simple systems, it gets plus few gigabytes of RAM in computations. So it is very demanding calculations if we use full relativistic approach. How we can approximate external potentials? This is our pseudo potentials, which we used in quantum space. So pseudo potentials method. When we take when we split the potential created by nuclei and by atom, so atom plus electrons, we say that we have some valence electrons, and this valence electrons there. This valence electrons we include in the calculation. So when we calculate, for example, number of bands, when we want to estimate number of bands in our quantum espresso calculations, and nuclei plus non-valence electrons. So, and we say this that nuclei and non-valence electrons is some one entity, is some one potential. We call it pseudo potential. So it matches from some distance r from electron from nuclei. It matches with real system, but below this distance r, so closer to nuclei, it will be simplified to some function, to some simple function, because it's really computationally hard to include all. It's really hard to include all electrons and all nuclei into equation. And Hartree energy, just Hartree energy, it is rather simple, and exchange correlation. So this is the main topic. I have told you about local density approximation, the idea about it. It was introduced by Thomas-Fermi and then upgraded by Kohn-Sham, and then a few more times upgraded. Then we also discussed general gradient approximation. So here we have only constant electronic density in some region near point X. And here we also include gradient of electronic density. We can include the change. And also we this time we will consider these two methods, MetaGGA and hybrid functionals. And this is some tradition to show all these methods on some kind of ladder. And we start from Hartree-Fock theory, Hartree-Fock and Thomas-Fermi theory. They're here, they're ground. Heaven is full accuracy. We don't. So if, for example, we can solve Schrödinger equation with no error, we will reach full accuracy. We didn't reach it yet. LDA is the next level. It depends only on electron density. Then we add some gradient density. You see here, gradient density. MetaGGA. It's GGA plus kinetic energy density. We can show it in two ways. So this is kinetic energy, or this is kinetic energy density. Gradient of kinetic energy density. And you see that each step is based on previous step. So this step based on this, and this step based on this, and this based on Thomas-Fermi, so on some ground on some ground level. And then we also have hybrid GGA, hybrid potentials, and it's some mixture of all these things. They are very computational demanding, but they are rather useful when we want to calculate exact exact energy gap, and full non-local methods. What means local and non-local? So local, it means that we include only only one unit cell in our calculations. And for example, it works bad when we want to apply some external magnetic or electronic field, because this external field, it will be non-local. It will affect on all unit cells. And it also works rather bad for van der Waals interactions. Because van der Waals interactions, they are Kohn interactions, and they also goes far. So when we don't include this non-locality, and we include, for example, only one unit cell, we just discard all interactions with other unit cells, which created by these electrons, by this van der Waals interactions. And that's our topic. And now I will shortly discuss LDA. I have already told you about this approximation. So this is kinetic energy for a single electron. Then we can get some exchange energy in terms of this approach, in LDA approach. We can get some approximation to exchange energy. You see here it was 5/3, and here is 4/3, power of 4/3. We don't know the correlation energy. As I told, the only information we can get from it, it's just that it's the difference between this real energy and this. We don't know it. We don't know this real energy. So we can, so this definition tells us nothing about correlation energy. But what is correlation energy? If exchange energy is the nature of exchange energy is rather clear, it rises from Hartree-Fock when we change this psi functions, and it means that we should include this spin effects, so the quantum effects. For correlation, it means that the electrons, when they are moving, and each electron which moves, it affects on some other moving electrons. And it's really, I don't know, maybe it's impossible to include all these interactions on moving electrons. We can try to calculate it by some methods like Monte Carlo methods or some other, but it's also not a good idea to calculate that exact energy, because it's not actually exact energy. We can take it from experiment. So we have experiment, and we can somehow exclude it from experiment and then estimate. And here is general form with spins. And alpha and beta are electron densities for spin up and spin down. And this is whole exchange correlation potential. Very general form. It depends only on n, on electronic density, local density approximation. Some popular pseudo potentials for some popular functionals for local density approximation, and we have used in our calculation this Fermi-Zunger approach. So they can difference one to another in terms of efficiency, in terms of computational cost, in terms of time, and so on. They are still rather popular. So Fermi-Zunger PW 1992 gets like 1,000 citations each year. Second level, general gradient approximation. Kinetic energy with LDA, but for general gradient approximation, we take this LDA approximation and add some gradient of some kinetic and some gradient of electronic density. Because this approximation it's really unnatural. We don't have the same density in the molecule. But this approximation, it adds difference in kinetic energy, and we can more reasonably build molecules. We can more reasonably calculate some crystals. This exchange energy with an LDA, which I showed you previously, and this exchange energy with GGA, with this crazy term. It's crazy, but it's also computable. But maybe an R is hard to calculate, and this term can also be rather huge. You can see that we have this crazy constant compared to this. It's just 3 divided by p in the power of 1/3, and here we have this huge crazy constant. And general form. In general form, this exchange correlation potential depends on n and gradient potential. So we have improved LDA. It's some improved LDA because we have added some gradient, and that's why our system is more realistic. And here is some popular potentials. We have used PBE, and in homework for model and in final in final problem, I asked you to use PBE, but also in model you had to compare PBE outcome with Perdue-Zunger outcome. So LDA with upgraded LDA with GGA. And we will see that for some systems it gives a not huge improvement in terms of, for example, band structure, but it can give a huge improvement in electronic density terms. And now we are moving further. We are moving to third level, to MetaGGA. So as I told, that each level depends on previous level. So MetaGGA is some improved GGA. And you see the guy, yeah, John Perdue. We have Perdue also here. So Perdue was here in Perdue Barker-Esenhoff. It's one of the most cited. It's one of the most cited articles. See how huge amount of citations, and he created this general guided approximation. And then he moved further. He tried to improve this approximation. And what he have done? If we have LDA, which depends on uniform electron gas, spin up, spin down, GGA all the same, but with gradient, and Perdue proposed to add some electronic, some kinetic energy density term. So it will be looks like this in very general form. It's just gradient of the functions squared, and then we calculate this term. But in this way, in this form, it's really hard to calculate it, and we should show how it looks like in electronic density terms. So it's some general energy approximation. This is LDA part, n in the power of 5/3, plus GGA part. Here is kinetic energy density. And this was the idea behind this MetaGGA idea, because this method, and why it calls MetaGGA. So because it goes beyond GGA. We have GGA here, this LDA plus gradient, we have GGA, and we go and we improve it. We add this kinetic energy density, because who told that kinetic energy is constant in this of electrons? It's not constant. So it will be changed in because electron affected by nuclei, by other electrons. That's why its kinetic energy also changed. And we had to we had to include it in some way. You see how we are moving from very simple homogeneous electronic gas to rather hard systems. And what is the idea behind this GGA? So how it improves our calculations? Here you see some exchange correlation, exchange energy exact. It means that it was created from Hartree-Fock with all these psi functions. And you see that LDA, it overestimates the exchange. This is exact, and this is LDA. Then we go to GGA. GGA is much closer, but it underestimates it on some amount. And MetaGGA is closer than, so you can compare to 2,600, almost 2,600. So they are rather close. We have improved this exchange function, but it's still not ideal. And correlation terms. Correlation term. Correlation terms. I don't see with what term we can compare here in the okay, never mind. You see that LDA, it underestimates correlation a lot. It was last lecture I have told you that it underestimates it on hundreds of 200%. But usually this correlation term is not huge. That's why we can. That's why when LDA overestimates exchange energy, here it overestimates it on 400. 400 R on centimeters squared. And underestimates it in 500. So when we edit, we get a rather good result. That's the secret of LDA success, because we have huge error here, we have huge error here, but this error goes in different directions, and that's why we have rather good result. But GGA and MetaGGA, they are even better. But you see that MetaGGA, it changes, so it's comparable with GGA. It is almost the same. So it's not so good for creation, but it is rather good for exchange. Atomization energies, kilocalories per mole. We can also compare it. This experiment, 109. So atomization, it means that we can take this molecule and remove these atoms. So remove the atom. And you see that, yeah, for hydrogen, MetaGGA is not okay, but for other systems, it's rather good. MetaGGA also gives mean absolute error, 31 for LDA, 7, almost 8 for GGA, and only 3 for MetaGGA. So it improved, but really not dramatically. It's really not what we wanted to see. I want to see 0, but we see just 3. 3 is good, but it's not ideal. And we had to move further to do something with this. But with each of this step, we approach to the real system. And this is scan, very popular as by now potential. Here also we see John Terdy. So he is co-author of almost all successful functionals. That's why he had 300 citations. And it's some abbreviation, strongly constrained and appropriately normed semi-local density functional. 2015, it had 2,000 citations last year when I made the screen. And what's the improvement? For example, here we see this band structure for some system. And for here is LDA. Here's LDA. As I told you that LDA, it underestimates band gap. So band gap calculated by LDA much smaller than than real. Okay, why do you think it happens? It happens because LDA works with homogeneous electronic gas, and the homogeneous electronic gas is a good approximation for metals. But band gap is some feature of semiconductors. That's why we can, of course, we can calculate some semiconductors with LDA, but it's not ideal. So we will have this error. But PBA slightly improves it, but it also, but the nature of PBA, what is the nature of PBA? Is LDA plus something. It improved it, but not, but still we don't have ideal result. And here we have scan with direct measurement. You see that scan rather good for band structure calculation. Scan, and it's rather fast. So it has it demands computational time almost as PB functional, but it is rather good for all the systems. Here are some also comparisons between scan and experiments, and you see that, for example, we want to calculate energy gap, e.g., for these systems, barium TO3 and some other things. Barium TO3 is very popular material for solar cells. LDA 172, PBE 173, experimental 338, scan 2 and 13. So it's not exact, but it's better than PBA and LDA. And HCA, our next hero, Heisenhoff. It's hybrid functional. It gives us almost experimental, but it's some kind of, it's really hard to use this hybrid functional. For another system, Lumbum TO3, 137 LDA, PBE 188, real system 3 and 6, and scan 208. So we can see improvement, but it's rather far to experiment. But it's better than previous potentials. I don't remember what is X, H, and T. Maybe it's some, I think it's different systems. Here is formation energy of some clusters. And you see that scan, where is it? It's green. It gives us almost experimental data. PBA, HSTA, hybrid functional, it gives better data in some systems, for example, here, but here not. PBA and LDA is the loser of these calculations. PBA is better, it's the same, is better than LDA, but it loses to scan. So if you will want to calculate something using MetaGGA, I recommend you to use scan. Okay, and what about hybrid functionals? Our last level by today. Hybrid functional is some kind of mutants. It consists, here is some exchange correlation energy proposed by Becker in 1993, and it consists of LDA, exchange correlation. It consists plus some empirical parameter, we don't know it. Here is some X exact, so it's calculated by some Monte Carlo, or maybe it gets from some experiment minus this LDA. So we construct its LDA term plus exchange energy plus another part of exchange energy from B88, it's GGA functional, and plus correlation part of PW91 with some parameters. So this is not very natural. This is not very natural. As you saw last times previously, we took for LDA, we took electronic density, then we took gradient of electronic density for GGA, and then we took gradient of kinetic energy for MetaGGA, and it was normal. I mean, it was improvement of our understanding of the nature. But here we take parts of some potentials, some good potentials, like B88, we take only exchange. But correlation, Becky thought that the correlation part is better in PW91. And he also used these empirical parameters, which we have to estimate with some experiments, for example. One of the first hybrid functions was PBE 0. PBE shows that we use it based on PBE for GJ, and 0 means that it was published in 1999, but it refers to 2000, 0. Exchange correlation in this PBE, it consists of Hartree-Fock exchange. So we take this Hartree-Fock part, this for exchange energy. Then we take some part of PBE, but you see, it's how to say it? Here we have A, but here we have 1 minus A. So they have to work together. It's not that I take all the part, but all this exchange term, but I take some part of this exchange term, plus correlation term. So in PBE 0, what was improvement? Improvement was in the exchange term. They improved it by adding some part of Hartree-Fock. And how do you think why we add this Hartree-Fock? So what's the problem we should solve by these hybrid functions, and why we can try to solve it by adding Hartree-Fock? Because Hartree-Fock, it was like 100 years ago. It was not. It was there was no computers at the time when Hartree-Fock was invented. How do you think why we want to improve it, the system with so we want to get realistic band gaps. Previously we couldn't get the exact band gaps, but with hybrid functions we get almost exact band gaps. So what's the reason why we can add Hartree-Fock and then we give rather realistic band gaps?
Maybe it's pretty simple, and so it's easy to like empirically modify it with some magic constants in it.
In one way, yeah, it's empirically modified in this A. What was the minus of all the GGA, MetaGGA, LDA? Because it was based on homogeneous electronic gas, but Hartree-Fock don't based on a homogeneous electronic gas. It's just psi functions. It is rather hard to calculate it exactly, but that's why they demand so much time. This hybrid functions, but it gives us only psi functions. It don't give us some homogeneous electronic gas approximation. That's why it's closer to reality. But Hartree-Fock don't give, but solely Hartree-Fock don't give us really good results. That's why it was not very popular. So it was invented, but it was a good idea, but it didn't get us really good results. And that's why we had to improve it. We improved it by this PBE part and correlation PBE. Because for Hartree-Fock, it was no correlations. There's no correlation for Hartree-Fock. Then, okay, this PBS0 was created by Enzerhof. This is the guy from PBE, Perdi, Burke, Enzerhof. E in PBE, it's this guy. And Suzeria. And now we have another potential created by these guys, two potentials. Suzeria, Enzerhof plus Hyde. So HSE 0306. It means in 2003 and 2006 it was published. It's not a big deal to name this potential.
Looks like Purdy finally retired.
No, he didn't retire, but I don't know why, but he don't work with this hybrid functionals. Maybe he don't think that it's a good idea because, as I told, it is rather unnatural. The ideology of Perry was to create, so Perry, Burke, Eisenhoff was non-empirical set of potential, so functional. He created non-empirical potential. That's why it is so popular, because it's very natural, it's close to nature. Then he created MetaGGA. It is also almost non-empirical, but this thing is highly empirical. Maybe it contradicts to his ideology. I don't know. So we can ask Perdi about it. So what was the? Okay, I think I should move it here. Because if I will close it, there will be no video in sale. Okay, what was the idea of this HSE? The idea was to split all the output into short range and long range. What is short range? It's some interactions inside unit cell. This was the problem which I told you. We had to go from unit cell to huge amount of unit cells. But it's hard because all these methods they based on some condition, some border conditions that and it's very easy to use one unit cell, but it's not easy to use more than one unit cell. And these guys, they propose to take two terms, short range and long range term. So they split it. They split the outcome and what's the functions? So this is function RC x. It looks like this, and minus you can try to imagine it minus this. So they tell us that this is short range term, and opposite to it we have long range term. And these functions, they satisfy some error functions. They satisfy this condition of non-locality. So we can do this thing. This is PBA.
Can you show like a long range term? It's covered by development. Can you move to the
it's the same. It's the same.
Okay.
You see, they are connected with this formula. With this formula. And this is short range because you see we have some zero here, and we don't go further we don't go far from the zero. And now I want to show you the difference between PBA 0. So it's a function of these guys, Suzeria and Enzerhof. And now we can split this PBA 0 into this short range and long range. I just the difference between these two equations is just I added in all terms. I just added Hartree-Fock short range, Hartree-Fock long range. The same I made with PBE short range, long range, and the long range. So I can split it in this way, short range and long range. And what we have here for HSE 06. So we have short range Hartree-Fock. So they say that we will use for unit cell and the neighbors of this unit cell, we will use this Hartree-Fock. then we add some short range PBE exchange. So we create this part only with Hartree-Fock plus PBE. Then we add some long range interaction, which will be created by PBE. And we just have this correlation energy, which don't split into short range and long range. And now, when we work only in short range, so in local, it means that long range goes to 0. Yeah. When we this goes to 0, and what do we have? If I will and I have when we are going to 0, we have only this. We have this relation. I have this term Hartree-Fock. I have this term because it saves because it's short range. But long range PBA goes to 0. We just discard it. There is now in PBA 0 such term, and just correlation. So when we work only in short range, we will get PBA 0 exchange correlation. If we will go to long range, in long range we will have PBE plus. So in long range we will have PBE exchange and PBE correlation. So at short range we have PBA 0 only in short range, only in long range we have GJ, the common GJ, but we combine them and get such HCA 0, 6 material. And you see distance from center cell in angstroms. We can it's short range and Hartree-Fock. This is Hartree-Fock, yeah, and this is short range. So our short range interaction, it goes to 0 when we goes to more than 10 angstrom from our cell. Hartree-Fock don't go to 0. So it's second nearest element, central atom. But I think of this. I think that this mem shows exactly the nature of this hybrid functionals, because you see it's some combination of this short range parts of long range parts, combination of LDA plus JJ plus Hartree-Fock, and that's why it's so hard to calculate it. It's hard because we don't calculate exactly one unit cell. We calculate some neighbors of this unit cell, and it is very computational demanding. But we have very good band gaps for it, because this empirical potentials, because this all this empirical A's, all these empirical parameters, we can play with them, and for some system. So we study some perovskites, we can play with these empirical parameters to show the good perovskite energy gap. And I have shown you last lecture this picture. I think this is a great picture, and I can show it again. SPB plus GW. GW is green functions. It's first level. I don't tell about it because I think that it's very hard to tell about it. We have band gaps very underestimated by PB. For example, magnesium O, it's 4 by PB, but in reality it's rather 6, something like this. Diamond, it shows almost 4, but in reality it's almost 6. So PBA is not good for this for band gap calculations. LDA is even worse for band gap calculations. You see how strong it underestimated. But HSC is these triangles. HSC is good. it's rather good. You see that these triangles, they are very close to the line of exact of experimental data. But of course, methods from above, from fifth level, so Gabor functions is fourth level, and GW methods, some quasi-particle methods, they are on the fifth level. They gives us better results, but they are really crazy, and I even don't sure if we can call them DFT, because they are very far from all the stuff which I told you in this course. And maybe, and this is slides to summarize what we have learned. We have moved from Hartree-Fock to LDH, MetaGGA, plus electronic density, gradient electronic density, gradient of kinetic energy density. Then we made all this combination of all these levels to work with some particular systems because they are highly adjustable. We can change this. We can change the empirical parameters, and it's one of it shows its artificiality. So because this is some artificial functions, and it was some work a few years ago, maybe 5 years ago, that if we will play a game with this empirical parameters, so if we will take some system, then we choose empirical parameters, and we say, yeah, we got this energy gap. It's very cool that we got this energy gap. It is not good for electronic density. So maybe energy gap will be okay, but electronic density will be crazy. So we have to be very careful when we play with such things like hybrid DJs. We have maybe hundreds of such DJs. I showed you just the most popular, like HSC 06 and PBA 0. They're still rather popular about them, and they was the first, maybe the first, and they show the idea behind this GGA. And for today, it's all what I wanted to say. Maybe you have questions. Okay, thank you for attending this course. I hope you will pass your exams.